Hi, I am Melissa Peters, and in this very brief presentation I'm going to talk about this research paper here below. So in essence, the paper is about how we can reduce the use of water by using wastewater and applying that to concrete. You probably will have come across the UN Sustainable Development Goals. And goal number 6 is really focused on that everyone has access to clean drinking water. And while that might seem very logical to someone where I'm based here in the UK, that's clearly not the case everywhere. So what we're trying to do here is to maximize the use of the water and to see some value in the waste that we produce. And in this case, I'm going to show how we can apply this to concrete. Now, the team that I'm working with here, it's very multidisciplinary, so I'm mainly an analytical chemist and I work in advanced materials at Newcastle University, but I work together with Sylvia Tedesco at Manchester Metropolitan University and Dr. Ahmed Ash at Leeds Beckett University. And I used to be based in Manchester as well, and we all met via a meeting with the Royal Society of Chemistry where this project was discussed. So this is not about just the water waste, but it's also talking about other waste that we have. So in this project, we're not just looking at the waste of water, but also at solid waste. And here I need to talk about the process of anaerobic digestion. So I think we all know there's a tremendous amount of waste, so solid waste that we have, and we can't really use that waste at the moment because either we need to deactivate the pathogens or we're not quite sure how to convert the organic compound into something useful. Now, in a kind of approach to do this, and this is really like a circular economy approach, because we take waste that comes either from animals or from agriculture or maybe from food, even municipal waste, and we put this in what we call an anaerobic digester. So what this does, as the name implies, it's anaerobic, so there's no oxygen there. So it's able to convert that waste into biogas, and that's we also refer to this as biomethane. And this gas can then be used for heating, for electricity, and that's very useful. Now, while this process is very good in the sense that we take some waste and we create energy from it, unfortunately still around 20% ends up as like the solid waste, and that's what we call the digestate. And this digestate, in this project, we're trying to make a full circle of this, where we start off with waste, we create energy, and then the waste that remains behind, we're also trying to put that into something useful. And this waste still contains a lot of valuable organic compounds. And the most common route to use this, and you would often see that a lot of these plants, they actually sell this waste again, is in a liquid form, is that it's used in fertilizer. But some of the problems with this is that it needs to be compliant with certain guidelines, which might actually cost them money in order to make sure that it is according to the standard. But also we're not quite sure of the buildup of, like, for instance, certain hormones or pesticides, and that ends up again in the land. There are some alternatives if you want to use this as a solid, but that does mean that you need to remove all of the water again, which obviously consumes energy, and that can be, for instance, for bioethanol production or using an animal feed or to build some composites. Now, what we're interested in is using this in the liquid form, so that means that we wouldn't have to remove all of the liquid itself, and applying that to concrete. Because what you might not know is that concrete is a very thirsty material. So you use about 100 liters of water to produce a cubic meter of concrete. And our research question here was really, because we also know that the concrete industry and the building industry plays a very important role in global warming, is we can replace all of that water that's used to produce concrete with the digestate. And there are certain challenges here, which I will show. First of all, the workability. And that means that we need to have a material that we can actually work with, so it needs to be liquid enough in order to be molded. Some problems can be that there might be sulfur in there, which I will show later on can attack the concrete at a later stage. And we need to make sure that it retains its mechanical strength. And within this paper, we show some of these preliminary results. And we use different mixtures. So we had a normal batch where we just use the normal water, and then we started mixing that in with the digestate. And the digestate is quite liquidy-like, so that made it possible to do this, and it had a solid content of around 10%. And the type of waste that we use, this might also be important, because you might not be able to do this, for instance, with municipal waste. This came from waste from the brewing industry. Now you can see that we produced a concrete here, and what we did is we analyzed what was in there. So we looked at the elemental composition, we looked at the ash content, the solid content, but also what type of ions were there, because that might have an impact on the mechanical strength later on. And what I certainly didn't know at the beginning of this project is that concrete doesn't have its maximum strength straight away and then it slowly goes down. It actually works the other way around. Because of the processes taking time, it actually grows stronger. So therefore it's very important to test the mechanical strength over different time periods. And then you can look at certain guidelines, and you can see whether the concrete actually meets these guidelines and whether it can be used for certain applications. So depending on what type of building you have, and I think you can imagine if you have, for instance, a bridge or a house, there will be very different rules for the concrete. But what we saw is that, and here we can compare it to the batch. Well, the first one, number one, was when we only used the water, that there was no real significant impact of adding the digestate to the strength, except for when we only used the digestate. And that was a very good first result, but obviously this was only done for about 28 days. And here we need to consider why the water is important. In order to think of an actual application of this project, we need to think about why water is important and how that can actually lead to the failure of concrete. Now, if you use less water, actually the material you'll get is much stronger. But if we don't have the water, then the material doesn't flow, and then we can't mold the concrete into shape. So the problem is then if you use too much water, then you can form these pores, and these pores are especially susceptible to certain types of attack, such as a sulfate attack, which I will show later on. And these pores, they can grow over time, and that can lead to failure. And a good example of how you can get this cracking and this pore formation is shown over here. And this is particularly due to the sulfate attack, where I talked about if there's some kind of sulfur present, this might occur over longer time periods, and 28 days certainly wouldn't be enough to pick up on this. So that's why when we use the waste, we need to be very careful about the elemental composition and what's in there. And also the type of sulfur is very important. So we use techniques such as, for instance, ICP-MS to determine what was in there. Now, if we want to prevent this cracking, we need to go to water content, but as I said, that might have an impact on the workability. We can think of, for instance, alumina, reducing that, but also the amount of base that we use might be a way of how we can prevent it. So this is a very brief presentation where I touched upon the concept of circular economy. And if you want to know more about this particular topic, then have a look at this recommended video. But what we were doing actually here, we had waste and we produced energy from this, so from this anaerobic digestion process. And we took the waste from that process, so the digestate, in order to apply it to something else to really come full circle. What we do need to know is if we have the concrete, we need to understand more about the long-term processes, and for certainly we need to figure out more what happens to the mechanical strength and analyze the structure, for instance, see this pore formation. We would want to do leaching tests to see if we can add any leaching of certain ions in there, and we need to have, even though we tested 3 different batches, so we did the measurements in triplicate, we would need more to evaluate reproducibility. And finally, very important, is you need to think about how you convince someone if they would actually adopt the technology. And therefore techno-economic analysis would be very important, because we need to figure out how much energy, but also how much it would cost in order for this process. And we need to make sure that this would be appealing to whoever would want to use this. Thanks very much for watching.